go, Science Alliance. All right, IGCSE. It's lesson 10 of IGCSE Physics. We're doing momentum. I love this one. I love all of these forces lessons, but I really like this one. To try and use a real life example of momentum, I asked you to bring with you 3 pens. I was trying to get across that they just had to be identical pens, but the colour didn't matter, right? They just need to be the same sort of design, and it's better if they're round so that they can roll. What I want you to do, I will show you on the screen. I don't want you to actually do it yet, in fact. I mean, you can set it up in front of you. I just want you to imagine it's a thought experiment. Do not do it. Don't do it. You'll ruin it. This is a thought experiment, first of all. Imagine you've got 2 pens side by side on the table. There we go. And then put another pen about 20 centimetres in front of one of those pens. Don't set it up now if you're not going to be able to resist doing it. Imagine, please, if you flick the red pen, what do you think will happen when it collides with the blue pen? And here are your choices. Is it A, they will both immediately stop? B, they'll roll together at the same speed the red pen was travelling at before? C, the red pen will move backwards and the blue pen will move forwards? Or D, there should be another L in that, they'll roll together at a slower speed than the red pen was travelling at before. Right? The green pen is just there for reference, okay? So I'll make this more interesting. Look, I've actually got it set up here. I even got the colours right, but I don't want you to do it yet. I just want you to think about it. Please don't do it. So I've got a red pen and a green pen next to each other, a blue pen slightly in front of the red pen. If I flick both of those, I can't because I'm holding my camera, but if I flick both of those, the green pen is just there to show you how fast the pen would travel if there wasn't anything in front of it. When the red pen hits the blue pen, what's going to happen? Are they both going to stop? Are they going to roll together at the same speed as the red pen was travelling at before? Is the red pen going to move backwards and the blue pen move forwards? Or will they both roll together at a slower speed than the red pen was travelling at before? This is a thought experiment. Please don't actually do it. And then I'll teach you about momentum and then we'll come back to that. And I'm wondering if you'll be more confident about your answer in the end. All right. Your actual real starter question is, a hippo and a hamster both charge towards you at a velocity of 5 meters per second. Can you tell me, number 1, which one is going to hurt you more? Number 2, can you give me a reason for your answer to number 1? And number 3, is there anything slightly wrong with my starter question based on previous lessons? That's not a leading question. You might decide that there isn't anything wrong with my starter question, or is there? You have to remember something. No, I'm not going to tell you. I'm not going to tell you. Imagine that there's a hamster and a hippo both running towards you at a velocity of 5 meters per second. Which one is going to hurt you more if it hits you, and why? You probably answered the first one straight away. Can you give a reason? There were some really interesting reasons being given on Facebook. When I did this lesson yesterday, people were talking about density. People were talking about forces. People were talking about mass and weight. I will be silent. I always say that, and then I'm not. I'll be silent for 20 seconds for you to just consider question 2 and 3. Is there anything slightly wrong with the question? A hamster and a hippo charge towards you at a velocity of 5 meters per second. Which one is going to hurt more and why? All right, let's do question 3 first. Is there anything wrong with this statement? Well, I thought you might say, hey, that says velocity, and I know that velocity is a vector. Do you remember this? Quick revision session. Oops, that's just my blinds. Do you remember we have talked about vectors and scalars before? So a scalar is something that you can just describe with a number and a unit. So speed is a scalar. If you say how fast are you running and you say 10 miles per hour, the 10 is a number, the miles per hour is the unit, and that is a description of speed. But if it's a vector, you need to add a direction as well. You remember this? So we've looked at how like force is a vector. So you've got to give a number, 10, a unit, newtons, but you've got to really give a direction as well. And velocity is a vector. So you would have to say running 5 meters per second to the left or northeast. But I've said a velocity of 5 meters per second, a number and a unit, but I have also said towards you. So my answer is, I don't think there is anything wrong with that actually, because I think a direction has been given. The answer to 1 and 2 is the hippo is going to hurt you more because it's harder to stop. And this idea of like unstoppability, how difficult it is to stop something, is called in physics momentum. So next question, because I think you have got a little feel for momentum just from real life, even if you've never studied it. Imagine you're running down a hill and a deer walks out in front of you in that lovely calm way that animals do. You're legging it down a hill, all right? You're running really fast down a hill. A deer just wanders in front of you. What is going to make it harder for you to stop? Choose as many of these as you like. Number 1, wearing a heavy rucksack. Number 2, the weather being warm. Number 3, if you were running really fast. Number 4, if you were running very slowly. I don't know if number 4 is that possible in real life? Anyway, this is a thought experiment. If you were wearing, picture it please. Actually picture yourself running down a hill. A deer just wanders in front of you. If you've got that heavy backpack on, is it going to be harder to stop or easier to stop or no different? If the weather's warm, does that make a difference? If you were running really fast, that make it harder or easier to stop? If you were running really slowly, harder or easier to stop? Because all the answers are going to lead us to the equation for momentum. It's quite a simple equation, this. It is 2. 2 of them would make it harder for you to stop. And they are, if you were wearing a heavy rucksack, then it would be much harder for you to stop. And if you were running really fast, it would make it harder for you to stop. And that leads us nicely to the equation for momentum, which is momentum equals mass times velocity. Momentum, how hard you are to stop, is the same as your mass times your velocity. So if you have seen previous lessons, can you tell me what are the units of momentum? And if you saw last week's lesson on Hooke's law, can you tell me what this kind of relationship is called? I'm really sorry, this is a lesson where last week in the live we had technical difficulties and you couldn't watch the Hooke's law lesson, could you? I sent you to a recording. So if you don't know what this kind of relationship is called, you're about to find out. But you should be able to tell me the units of momentum now, really. So momentum is exactly the same as mass times velocity. So the units of momentum are exactly the same as the units for mass times the units for velocity. You've done a lot of brain exercise already, so I'll just go through this one. The units of mass are the kilogram, and the units of velocity are meters per second. So if you times those together, you get kilogram meters per second, and that's what you say. Be careful, it's not kilograms per meters per second. You're not dividing mass by kilograms, it's just kilogram meters per second. You'd think they'd have called it something catchy, like giving it a nickname like the Newton or the Joule, but they haven't. It's just kilogram meters per second, and that kind of relationship is directly proportional. We learned last week if mass stays the same, then if your velocity doubles, then your momentum doubles. If mass halves, then momentum halves. So this is a directly proportional relationship. Whatever happens to one side happens to the other side. All right then, have you understood that? Can you tell me please? I hope you appreciate that I did actually look up these animals and what their masses were. What is harder to stop? A 10 kilogram honey badger rolling down a hill at 1 meter per second, or a 1 kilogram moon rat, it's a thing, rolling at 10 meters per second, okay? And momentum equals mass times velocity. I'm going to do it on the board as well. Can you write that out I want us to practice writing out our working, because it's good for you to learn how to do it for exams. Right, have you done that? So the answer is, I forgot to put so many R's into this lesson. Did you get that the answer is that they are both the same amount of difficulty to stop? They've both got the same momentum. And this is how I would write it in the exam. Momentum equals mass times velocity. So the badger's momentum is 10 kilograms, its mass, times 1 metre per second. That's its velocity. We don't need to write directions. It's not relevant here. So the momentum of the badger is 10 kilogram meters per second. But the rat, in inverted commas, because the moon rat isn't a kind of rat, but anyway, the moon rat, its mass is 1 kilogram and its velocity is 10 meters per second. So you times those together, you get exactly the same answer, 10 kilogram meters per second. Which is why hippos charging at you quite slowly will really hurt you, but bullets, which have a very, very small mass but are travelling extremely fast, also hurt you, because you can have a very high velocity and a small mass, or a very high mass and a small velocity, equal amounts of unstoppability. So yeah, they were both equally difficult to stop. All right then, have you really answered that? Let's have a go. First of all, we can't talk about the symbols. So the symbol for mass, go on, what's the symbol for mass if you were just going to write this equation out as letters? Be careful, it's not the same as the units, right? So the unit for mass is the kilogram. But the symbol for mass, if you just want to write mass in a quick way, is a little m. The symbol for velocity is a little v, and the symbol for momentum is a p. Yeah, sorry about that. So if you want to write this equation out quickly, you could just write little p equals mv. I'm trying to remember why it's a p. It's the word that like means unstoppable in like Greek. I can't remember. Anyway, not to be confused with a symbol that looks a bit like p but isn't a p. We'll learn about that when we get to density. Momentum, it's actually a little p. All right then, have a go at these questions for me, please. I've said do and do if time. If you're watching live, then I'd really like you to do the ones in green, and depending on sort of how good you are at maths or how well practiced you are, how much further reading you've done, you might want to do the orange ones as well. Obviously, if you're watching this on catch-up, you can just pause it, can't you? That's the great thing about catch-up. So a car with a mass of 1,000 kilograms travels at a constant 30 meters per second. What is its momentum? And if you want a tiny little bit of practice at rearranging equations, the next question is, a cat running at 3 meters per second has a momentum of 6 kilogram meters per second. What is its mass? And if you want to try the slightly harder questions, what's the momentum of a car with a mass of 2,000 kilograms, which is travelling at 5 kilometers per second? And, oh, that one is hard, actually. I should have said, for the last orange question, a ball weighing 20 newtons falls at 5 meters per second. What is its momentum? This is our weight equals acceleration due to gravity times mass, right? Weight equals mass times little g. You have to remember that equation for that. Say that little g is 10, just to make the maths easier. At your IGCSE, you'll have to say that little g is 9.8, but just say that it's 10. And if you don't know what I'm talking about, you need to watch the difference between mass and weight lesson. I'm not going to go into that here. And then for the extra challenge, imagine that you are just discovering this equation for momentum. Why is it mass and not weight? Why, if you were discovering this equation and about to tell everyone, why couldn't you say momentum equals weight times velocity? And I'll give you a clue in a minute. I'm going to do this maths alongside you. And I'm going to write down my working, which I want you to do as well. Okay, some of you are working fast. I've still got one more question to do. But here's your clue. For that last one, why is it mass and not weight? Some people are saying, oh, well, it's because momentum is measured in kilogram meters per second and force is measured in newton, so it wouldn't work. But why couldn't momentum be measured in newton meters per second? Can you think of a situation where something could have very little weight but still have a lot of momentum? That's your clue for that last one while I get the question 4 done. All right, I've finished, so I'm going to give you a few more seconds and then I'll go through the answer. Like I say, I'm not expecting, if you're watching live, I'm not expecting you to have finished them all. That's not really the point. I tried to put enough questions in that people who go fast get a bit of a challenge, but that everyone gets to do some of them. But I will be silent for another, I don't know. There's no point saying a number is this, I'm just guessing. I'll just be quiet for a bit. All right, let's go through the answers then. There's more questions for you a bit later on, so you'll get a bit more practice if you didn't quite finish those. A car with a mass of 1,000 kilograms travels at a constant 30 meters per second. What is its momentum? So I would always write down the equation, always in the exam. Here it is. I've just put P equals mv. You okay with that? P means momentum. Momentum equals mass times velocity. So the momentum of the car is going to be its mass times its velocity. 1,000 kilograms times 30 meters per second. And the answer is 30,000, 30 times 1,000, kilogram meters per second. You better have written down the units. Just very good practice. Okay. Always write down your units because then you can see if you've gone wrong. Question number 2, you got to do a little bit of rearranging. This cat has got a velocity of 3 meters per second and a momentum of 6 kilogram meters per second. What is its mass? So again, I'm writing out my equation because you never know, even if you rearrange the equation incorrectly, you might get a mark for just knowing the equation. So momentum equals mass times velocity. Do you know the therefore symbol? It's really cool, this one. I don't know. I always feel like a pro using this. 3 little dots in a triangle means therefore. So if P equals MB, therefore M equals P divided by V. You need to be able to rearrange equations for IGCSE. So the mass of the cat is 6 kilogram meters per second divided by 3 meters per second. And I've put a 2 here because just to show you what I would always do in an exam, I would always check to see if my units work out. So I can see here, I've got meters per second on the top and meters per second on the bottom. So I know that cancels out, right? 1 divided by 1 is 1, 3 divided by 3 is 1, 1 billion divided by a billion is 1. So whatever's on the top and the bottom cancels out. So the units that I'm left with are kilograms. And then this is especially helpful for A-level. If rearranging equations gets more complicated, you can go, all right, kilograms has popped out, is that right? Yes, because I was looking for mass. Excellent. And it's just a really good way of checking that you're right. Next one. What's the momentum of a car with a mass of 2,000 kilograms travelling at 5 kilometres per second? Did you get that the velocity was in kilometres per second, so you had to convert it into metres per second? So 5 kilometres per second is the same as 5,000 metres per second, and then you could plug into the equation. So 2,000 kilograms times 5,000 metres per second is 10 million kilogram metres per second. I have said It's not good practice because you won't always be able to do this. In this case, you could have got away with not converting and just saying 2,000 kilograms times 5 kilometers per second is 10,000, and then you just would make sure that your units match. So if you'd written that the units of momentum there were kilometers per second, you'd have probably been okay, but don't do that. Convert first. And the last one, a ball weighs 20 newtons, so it's getting pulled on by Earth's gravitational field with a force of 20 newtons, and it's falling at 5 meters per second. What is its momentum? So to work out momentum, you need mass and velocity. We've got its velocity. We don't have its mass, but we can work out its mass from that equation, can't we? I guess some of you will be saying, well, you didn't say it was a ball on Earth. All right, fine, it was a ball on Earth. So we know that the gravitational field strength is about 10. That's what I'm going to use. So the weight of the ball is little g times m. Again, you won't know what that means unless you know a bit about the difference between weight and mass. So I'm assuming that you do. So you can say that mass equals weight divided by little g, which is 20 newtons divided by 10 newtons per kilogram. So the mass that pops out is 2 kilograms. And then we've got the mass and the velocity. So it's just like the others we've done. Momentum equals mass times velocity, which is 2 kilograms times 5 meters per second, which is 10 kilogram meters per second. And did you get why it was mass and not weight? It's really difficult, that. There are scenarios, they're not very likely, but there are... Oops. Sorry, that was my battery low. It's not likely, but there are situations where something doesn't have any weight, but it's still got momentum. When we were talking about Newton's laws, we were saying what happens if you push something in space. Do you remember? We were saying how mass, for the purposes of your IGCSE, mass means kind of the amount of particles that are in a thing. So the mass of this mug on Earth is the same as the mass of this mug on Mars. It's the same as the mass of this mug as it is floating around in space. It's just like a measure of how many particles are in the thing. The weight of this mug depends on the gravitational field that it is in. So on Earth, this mug would be pulled on more than, say, if it was on the moon. So it would weigh more on Earth, right? But if this mug was floating in space, if it was travelling through space, you remember we talked about how if you like push something in space, then there's no particles to push back on it, there's no friction, so that thing will just travel forever. If this mug travelled through space and hit you, it would still hurt. You'd still have to stop it with your face because it's still got a mass and it's travelling at a velocity, but it doesn't weigh anything because it's not in a gravitational field. So that's why the equation is mass times velocity and not weight times velocity for that exact scenario, because you would say if it was weight, you'd say it wouldn't have a momentum because its weight would be 0, so its momentum would be 0, but your face would be able to tell its momentum is not 0. Right, I'm going to stop saying the word face because that's weird. I'm going to take you out into my hall to show you the classic physics teacher activity to demonstrate momentum because it's fun. So I need a football and a tennis ball, and I need you to be very forgiving of the state of my hallway because regulars know that I just had my loft converted and that, well, the whole house is still sort of suffering from the effects of the loft conversion, which is awesome. Not complaining about having a loft conversion. Oh, sorry, do you need to get by? I'm just going to be in this hall for a sec. Oh, are you going out?
Taking you out?
Yeah, but not right this second.
Well.
Are you getting her and bringing her back?
Oh, okay.
Thanks. Sorry, a quick meeting with my husband about who's picking the child up from school. Right, I've got a football here and a tennis ball. And first of all, I want you to see how high they bounce when I just drop them separately, okay? So, football, not that high. Maybe 3/4 of the height that I dropped it at. Tennis ball, far less bounce, isn't it? Tennis ball, not very bouncy at all. What's going to happen if I put the tennis ball on top of the football and then I drop them both at the same time? Are you ready? Classic physics teacher experiment. I wonder who discovered this. Well done, that physics teacher. I'll come down here so you've got a better view of the activity. Ready? Now, it's not working terribly well, but I'm actually quite pleased it's not working well because I'm not expecting it to work that well. I'll tell you why. But hopefully what you're seeing is the ball bouncing higher, the tennis ball bouncing higher than it normally would. Actually works better if I don't drop it too high. Oops. You ready? Are you seeing that? The tennis ball is far more bouncy. So just dropping it onto the rug, not so great. Dropping it on top of the football, hey, it's lovely. The reason that is happening, she was just going, oh, I tell you what, everyone on Facebook yesterday was saying, do it the other way around. Okay, I'll do it the other way around, yeah. No result. Did you see that? If you put the football on top of the tennis ball, the football doesn't bounce off in the same kind of fun way. Why not? It's because momentum is conserved, and we'll talk about this when we go back inside. But the momentum of the football is getting passed on to the tennis ball, and because the football has got a large mass, it is the momentum of the tennis ball and the football are the same, okay? But the football has a bigger mass, so it's travelling more slowly. So when the football passes on its momentum to the tennis ball has a smaller mass. So in order for it to have the same momentum, it's got to go faster. Is that all right? I'll do it on the board. Let's get it on the board. Oh, you got a little... You got to see my hallway. That was exciting, wasn't it? It's like a field trip. Oops. I shouldn't have tossed them away so cavalierly. I sort of needed those for this bit. Anyway, yes. I'll put this on the board for you. This is the important law of conservation of momentum, what you need to know for your IGCSE. Momentum is conserved. If two objects collide, the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. I'll explain what that means. Really, we should be saying that this is true in an isolated system, meaning don't think about any external influences like the force of friction acting on the footballs. Some of you might have been thinking about how padded the carpet was. We're just thinking about the two things that are colliding. So this is sort of not true in real life, but in a perfect world without any external forces, then it would be true. So yeah, just to go through that again, right? Little p, is that all right? Momentum equals mass times velocity. The football has a big mass, so quite a low velocity. If the football passes its momentum onto the tennis ball has got quite a low mass. So if the tennis ball is going to have the same momentum as the football, the tennis ball ends up with a higher velocity, which is why it bounces off. The reason I was saying that it wasn't working particularly well is because actually my football was a bit rubbish, and when I weighed them, the football was like 70 grams and the tennis ball was 60 grams, so they're actually fairly close together in mass. If you've got a football at home and a small ball, you can get it so the small ball goes really far, but obviously the mass difference has got to be bigger. Okay, I'm going to show you a question and just talk you through it. So I don't expect you to answer this one, but this is a good way, this is sort of a good example of how your IGCSE Physics might test you on whether you understand this law of momentum. So, I don't know, this is a terrible example. It's like it's the 1700s or something. A child riding a bike at 3 meters per second sees a 1 kilogram bag of apples and decides to grab them, the wee scoundrel. The bike and the child all together weigh, sorry, that says weight, doesn't it? The bike and the child together weigh 20 kilograms. So we've got a 1 kilogram bag of apples, a 20 kilogram bike and child. They're traveling at 3 meters per second. When they pick up the apples and speed off, what is their new velocity after stealing the apples? Again, assuming that they just sort of would be travelling at a constant velocity. I haven't explained this well, have I? What I'm trying to say is just imagine that the bike is travelling at, they don't change how much they're pedalling, okay? So you've got apples that are 1 kilogram, bike human 20 kilograms, travelling at 3 meters per second. You need the new velocity once the bike and the human and the apples are all one. You need to know this law that the momentum of the situation before the collision is the same as the momentum after the collision, all right? So first thing you do is you work out the momentum of the first situation, which means working out the momentum of the individual bits and then adding them together. So the easy one to do is the momentum of the apples. They don't have a velocity, right? They're travelling at 0 meters per second. So 0 meters per second times 1 kilogram they've got zero momentum. And the momentum of the child on the bike is 3 meters per second times 20 kilograms, which is 60 kilogram meters per second. So if you add all those together, you end up with the momentum before the collision in total being 60, all right? So now you look at this new situation, have we got the information that we need? In fact, we have, because you know the momentum before the collision is the same as the momentum after the collision. So if the momentum before was 60, then the momentum after is 60 as well. So you've got the momentum. You've got the mass as well, haven't you? Because it's just the 20 kilograms plus the 1 kilogram. So the velocity is going to be, well, you know that the velocity after is the new mass, 21 kilograms, times the momentum, which is 60 kilogram meters per second. So if you rearrange that equation, you end up getting the new velocity is 60 kilogram meters per second, the new momentum, divided by the new mass, which is 21 kilograms. And the answer you get is 2.9 meters per second. Phew. And if you were in an exam and you were checking that, you'd go, all right, so the velocity was 3 meters per second, and then they got more mass, but their momentum was the same. So you would expect them to be going a little bit slower. So I'd be happy with that answer. Okay, here is that question again with different numbers and different objects for you to see if you have got that. Okay, so momentum is mass times velocity, and the momentum of a situation before is always the same as the momentum of after the collision, if you're not thinking about external forces like air resistance and friction and heating effects and all that kind of stuff. So a car of mass 500 kilograms travelling at 10 meters per second hits a stationary, that means standing still or staying still, car with a mass of 2,000 kilograms. They stick together, but they keep moving. What is their velocity after the collision? I'm going to do this with you. If you're in an exam, quite often they will just describe it to you, and I would definitely draw a diagram before I did anything else. Draw a diagram to make sure you've got the situation clear in your head. How are you getting on? I don't want to rush you, but I have finished. I'll go through the answer with you. So, you know the masses of both cars, and you know the velocities of both cars. So to work out the momentum of the before the collision in total, you just work out the momentum of each car and then add them together, all right? So the momentum of the first car is 500 kilograms times 10 meters per second. And the momentum of the second car is easy because it's 2,000 kilograms times 0 meters per second because it's staying still. So really you're just looking at the momentum of the first car. So it's 500 times 10, which is 5,000 kilogram meters per second. That's what I've written here. Momentum before equals, and I wrote it out like this, 500 kilograms times 10 meters per second, that's the first car, plus the momentum of the second car, which gives you 500 kilogram meters per second. So that's the momentum before. And then I've written it down so the examiner can clearly see that I know what I'm talking about. The momentum before is the same as the momentum afterwards. And momentum equals mass times velocity. So the velocity afterwards is going to equal the momentum afterwards, I could have put, divided by the mass afterwards. You know what I mean? So the velocity that we're looking for, the velocity of the new situation where both the cars are stuck together and moving, we know the mass and we know the momentum because it's the same as the momentum before. So the answer is the new velocity is the new momentum divided by the new mass, which is 5,000 kilogram meters per second, because we just worked that out, divided by, be really careful, this is why you show your workings, it's so easy to miss out one of the masses. Don't forget we need the new mass as well. So it's the mass of both cars added together. So you end up with the new momentum, 5,000 kilogram meters per second, divided by the new mass, which is 2,500 kilograms, and you end up with, again, 5,000 divided by 2,500. It's 2, and what's my unit? So the kilograms are on the top and the bottom, so that's cancelled out. So my unit is meters per second. Is that right? Feverish Lara checks in her exam as time is running out. Yeah, I was looking for a velocity and meters per second has popped out. So that's a very, very good sign. Splendid. Right. So that is pretty much the end of the lesson, except, have you cottoned on? Can you finish this sentence politely? What is momentum? It's what is it? You got a clue at the beginning because we were talking about vectors and scalars, weren't we? What is momentum? Well, I think the easiest way to think about it, something I read somewhere, a scalar times a scalar equals a scalar. A number times a number is just a number, right? So 3 times 3, whatever, it's a number. But a vector has a direction. So you can imagine vectors as having little arrows. So a scalar times a vector is like a number times an arrow. And a number times a certain amount of arrows, you're always going to get an arrow in the end. Does that make sense? It helped me to make sense of it. So a scalar times a vector is always going to be a vector. So here we've got momentum equals mass times velocity. We know that mass is a scalar. It's just measured in kilograms, doesn't have a direction. We know that velocity is a vector. So the velocity's got like a little arrow attached to it. So a number times an arrow is always going to give you some amount of arrows. So momentum, I don't need to write it on the board because it's here. Momentum is a vector. Momentum has a direction. And it's really important that you know that because, especially if you're doing A-level, what will happen is you will have to think about the fact that if you are given a velocity in a momentum question and it's say 10 meters per second in that, sorry, it's my phone battery dying. If the velocity is say 10 meters per second in the forwards direction, if the thing ends up going backwards, what is its new velocity? Do you know how you would show that in a number? I think we've mentioned it very briefly. If going forwards, the velocity is 10 meters per second. If it changes direction and starts going backwards, its new velocity would actually be minus 10 meters per second. So especially when you get to A-level, you've got to be really careful that momentum is a vector as well. So yeah, if you're using a velocity and it says it went forwards and then it went backwards, whatever if they've given you a plus sign for going forwards, you'd have to reverse that and make it a minus sign for going backwards. I don't think you need to worry about that too much at IGCSE, but it's worth mentioning. That direction is important. Okay, so if I know it's been killing you, right? Finally, we can roll our pens and see what actually happens. But you probably won't need to do it now for realsies, because maybe you've learned enough about momentum to know what's going to happen. If you put two pens side by side and then you put another pen in front of one of the pens and you flick them, what's going to happen when the pens collide? They both immediately stop. They can't, can they? Because momentum before the collision is the same as momentum after the collision. And if they both immediately stop, that means they've got zero momentum. And clearly the first pen did have momentum, and that momentum can't just disappear. So it can't be the first one, right? You can't take a situation that has momentum and then just there be immediately no momentum. Not in an isolated system. They'll roll together at the same speed as the red pen was travelling at before. That can't happen either, because if they're rolling together, then the mass of our situation has doubled. So you can't have them being twice the mass and travelling at the same speed, because that would mean that there's double momentum. And again, momentum doesn't just like appear or disappear, it's conserved. The red pen will move backwards and the blue pen will move forwards. Again, that can't happen, because if the red pen moves backwards, that's like minus momentum, because it's travelling in the opposite direction. So it's actually like minus velocity, if you like. So it has to be D. They'll roll together, but at a slower speed than the red pen was travelling with. First of all, I am going to attempt to do this. I know that I shouldn't. I know it's just going to look weird, but I have to. I can't help myself. Ready? So the green pen is just there for us to judge the speed. All right. And there you go. Momentum, like absolutely proven by this robust, flawless physics activity done with household objects. Yeah, nailed it. All right, you lot. That is the end of your IGCSE Physics lesson on momentum. Thank you so much for coming. I'm aware that I haven't given you any homework for Hooke's law. If you are desperate for homework, I should have said this ages ago. If you go to my website, there's the new IGCSE Physics lessons, which I'm teaching at the moment, which are live. But I do have a whole past series of lessons. They're not exactly the same, but they're very, very similar. Usually the homework will be pretty much the same. So if you're desperate for homework, you can go to the archive section of my website, and there will be some homework for whatever topic you are wanting to do. I'm going to go over to my Facebook page now, because Facebook is where I post a little post when I'm live on YouTube saying you can't comment on YouTube, but you can comment on Facebook if you want to. So I'll just see if anyone said hello. Oh, maybe nobody has actually. Maybe I'm free to go. Weird. I can see you lurking. So anyway, if you are watching live, but maybe you don't have a Facebook account, thank you so much for coming. Oh yeah, look, no one has commented. Well, that's fine, because I'm going to talk at a conference at the Institute of Physics tomorrow, and I need to catch a train. So I'm going to go. So if you are lurking live, thank you for lurking. Continue to lurk, and I will see you next week. Oh yeah, thanks for liking this video. Someone's just liked this video. I never say that. Like and subscribe. I think it does actually make a difference. All right, yeah, thanks for coming, you lot. I'll see you next week. I'll try and get you some homework up on the website after this Institute of Physics conference that I've been asked to speak at. Like, they just need me, so sorry. But yeah, I'll try and get you some homework up there for the last couple of lessons as quickly as I can. Oh, it's hardly worth it now. There's hardly anyone watching now. But if you normally watch my human body lesson and my Lego story show live on YouTube, it's not on tomorrow, because I'm at the conference. It's on Monday instead. The times are the same, but I've had to shift it from Thursday to Monday. So I've got a live on YouTube human body lesson on Monday at 9 o'clock, and the Lego story show is on Monday at 10:30, all right? So do what you normally do on Thursday, but do it on Monday. If that means that you can't make it, I'm sorry, but it'll be there for watching on catch up. Okay, I'm gonna go. Thank you so much for coming. Thank you for liking this video. I'll see you later. Bye.